this session where we will learn about how to use AI, data, and digitalization for autonomous and remote operations. I am Saptarshi, I'm from Shell, and with me I have excellent set of speakers today, and they are bringing with them multiple years of experience throughout the entire value chain of energy and power. The importance of reliable and efficient operation in energy sector is unquestionable, right? And on the other hand, we see how AI compute came a long way in the recent past. We all see this transformation. While we see most of the applications of AI where people are using it for generating images and contents for social media, the real value lies exactly here, how we can use AI for making operations much more reliable, much more efficient. And that's why the discussion, the talk today is really critical for what we do. With this, I would like to invite our first speaker, Thomas Heinzerling. He is SVP from Linde, and he is going to share with us and enlighten us on unleashing the self-optimizing autonomous plant, how to do that, right? It's very interesting. Let's hear from him how we can unleash the potential of autonomous plant using AI. Welcome, Thomas.
A very warm welcome to the few survivors of the lunch break. I hope I can energize you to the extent that you will be awake at least after my session. What I want to take you through in the next 15 minutes is Linde's journey in using closed-loop AI control to run critical infrastructure. Can you move the slide? Okay, here we go. So as you know, in Linde, we are on this journey of remote and autonomous operations for about 15 to 20 years. We are currently running about 1,200 plants across 100 countries from 10 control rooms where one operator operates or monitors the operation of 10 plants. And we used classical advanced process control, classical real-time optimization, and of course, what you would call a process digital twin for that. I myself was responsible for the Asia-Pacific operations of Linde, which includes India. So this is not my first visit to India, but the first visit to such a nice place. And the outcome was that basically we improved the efficiency of our plants. We reduced the maintenance costs because we reduced the number of plants and the number of damages that operators were inflicting to our plants. And at the same time, we increased the reliability. But what we saw is that these systems to completely automatically operate a plant are quite complex. So we decided to try to take the operator out of the loop and to really move to this level 5, where we have automatic systems that really operate the plant. And the operator is only activated if there's an equipment failure or there's a major process upset or some situation that we did not foresee. So how does this work? And basically here you have a simplified model of our architecture where we would have a real-time optimizer that would determine which assets should run. And an asset could be a plant, it could be a pipeline, it could be a compressor station, and at what load should they run. The second part is, of course, then if you want to start up or shut down an asset, you need an automatic system. And in our case, we call this automatic sequence transition. So this is an intelligent sequence that emulates an operator and can start up machinery, can start up a complete plant. And last but not least, of course, you want to optimize the steady state operation of a plant, as well as you want to be able to move the plant into different load scenarios. And this basically we do with an APC. And what we noticed is that these systems become very hard to commission, very complex to maintain. So very often we had APC or RTO systems that were not running at the full power of their efficiency. And so we decided to look for systems that learn by themselves. We started with AI plant control. So this is a self-learning advanced process control that basically can replace a DMC, for example. And later on, I'll show you our newest child, which is the AI real-time optimizer. So this is a real-time optimizer that learns by itself to adapt to different scenarios, for example, different feeds, different loads, and things like that. So let's start with the AI plant control, which is something that we have developed about 6 years ago. We have about 12 years of operating experience across a number of plants. And as I said, we had two parts. So we have plants that have extremely non-linear characteristics, where we struggled with the classical linear model predictive control, so the DMCs or the profit controllers of the world. Specifically when we had large operating ranges, so large amount of different feeds, different modes in which they should operate. So that was the one problem. And the other problem that we had is that we were lacking advanced process control engineers. So since they were a scarce resource, very often I had about 60 different APCs running in my control room in Kuala Lumpur for Asia Pacific. And typically half of them were not running at the best efficiency because we didn't have enough capacity to maintain. So our task was to build something that can be implemented without disturbing the plant, because typically our plant managers were pushing back when we came. We wanted a very robust control. As I said, very often we supply chemical complexes, we supply steel mills, whether it's Reliance or Tata Steel here in India. And typically when we shut down, it's a major problem. So we wanted to have something that's very robust, also with frequent load changes. And of course, as I said, we didn't have enough advanced process control engineers. So we wanted something with very low levels that require low levels of maintenance. So how does this AI plant control now work? I mean, you all probably are aware how a classical model predictive control works. So you send your APC expert to site, they shake the plant, do step tests, typically much to the dismay of the plant manager who wants to produce and does not want to go to any specific cases just for the sake of tuning MPC. And that basically, if there is any major change in the equipment or any major change in the operational scenario, you have to do this again. So the AOPS AI plant control works differently. So what we do is we take historical data out of your OZPI or your AP2021, and we train the model of the APC with that historical data. We don't need to go to any specific operation case other than the ones that you run anyway. And then we basically, we would let it run in parallel to the operator for a couple of weeks to compare, does the APC or our AI PC, does it do the same things? Does it make reasonable changes to the set points? And then at some point, the AI PC would tell you, okay, I'm ready. You can basically take the hands off the wheel. And then the operator relaxes and the AI plant control takes over. And the great thing, which I was pretty surprised on during our journey, is even with major changes of the operating scenarios or even with equipment being down, the AI plant control learns new situations. The only thing that you need is a couple of days or a couple of weeks of operation data, and it will adapt to the new condition and still maintain the product specification, optimize the yield or the energy efficiency, depending upon what you're talking about. So this is an example here. So on the left side, you see the 21st of January. On the right side, it's the 3rd of February. And you see that over Christmas, this was a plant in Europe, something must have happened. So the green line is the process value. The yellow line is the optimal value. So obviously, the advanced process control did not work well. And so then we took the timing from the 23rd to the 26th, so between the two white lines, retrained the algorithm. At the moment where we activated the new model, you can see the APC straight away was able to regain the optimal efficiency. And that's exactly the way how this AI plant control works. So let me give you two examples where we were dragged into a pretty complicated project in the first place. So this was the oxygen supply for Europe's largest steel mill from ArcelorMittal in Germany. And they had the problem, they had about 20 different modes how they could configure their gas supply system. So several MPC projects had failed because at the moment where the step tests were over and the APC was running, operators decided to reconfigure the supply scheme and the whole journey started again. And the other problem is, you see it in the right lower corner, is the consumption is going like a roller coaster. So we typically have a required load change every 10 to 15 minutes. And basically what we did is we tried our system here. Implementation time was about 12 weeks, no step tests, no disturbance to operations so whatsoever. So we were constantly supplying exactly what the steel mill needed. And using the APC retraining every 4 hours in the beginning, 35% faster load changes, 1% improved energy efficiency, 2% improved product yield, and the whole project paid back in 6 months. And this was one of our first projects with a prototype. Let me give you another example here. So this was the supply for a chemical complex from Evonik. And the key problem was that the supply was super critical because we would have created a hazardous situation if ever the supply would have failed. And this means that I've never seen operators that were that paranoid and worried about creating any problem with the purity of their products. And this was the reason why they were very far away from the optimal configuration of the plant. Basically, again, this was an 8 weeks exercise. Again, no disturbance whatsoever to the production. If we would have done it, Evonik would have kicked us out straight away, you can imagine. So no step tests, no production other than the one that was required. And what happened here is AI plant control was able to stabilize the plant to an extent that the operators were willing to go much closer to the efficiency limit of the plant, which meant that basically we improved the product yield by 8%, reduced the power consumption by 1%, and afterwards we had operators that were much more relaxed and much more happy with us. And of course, you can imagine the profit of this plant went up by nearly 30%. So what's the benefit of AI plant control in a nutshell? Typically, we have a couple of % increase in product yield, a smaller number typically in energy consumption, depending upon what type you control. And I think the biggest benefit is you have very stable operation, which also enables you to move the plant faster. And what made us very popular with our plant managers, not so popular with the APC team, I must say, is because we don't disturb operations. But the key problem that we faced is that the implementation was so fast that the teams had a trouble to basically keep up with now dealing with a new system. And the other parts that we saw is experienced operations team. So this could be a shift lead, it could be the process engineer. They are able to trigger retraining by themselves, which means that our APC engineers, who were typically dealing with in the order of 5 to 10 plants, they can now deal with 20 plants. So now let's go to our next baby. So we saw the big success with AI plant control, which is pretty critical for operations. So we said, okay, real-time optimization requires a lot of qualification, takes forever. And I've traveled many control rooms and I saw a lot of ruins of very sophisticated systems, be it the Romeos or the Aspens or any other tools. So we were looking for something that is fast to implement and easy to maintain so that it can survive. What you can see here is a typical example for a steam cracker. I think you know the structure. So in the bottom you have a an APC. That could be anyone. So it could be a DMC, it could be Honeywell Profit Suite, it could be AI plant control. And basically the real-time optimizer is generating the set points for the APC. And basically what we did now is a self-learning real-time optimizer that is then running in closed loop, giving the key parameters to the cracker. And one of the key things is as we use neural networks as a model, we can run the RTO in a 1-minute cycle, which means all the backup that you typically use for in an APC, if ever the RTO doesn't work, or if the RTO, you can only run it once per hour, we don't need that. In principle, you have a value all the time. You have a value in minutes, and you always have a result because it always converges. So how does this work? Basically, the magic work is surrogate models. So what we will do is we will use 2 different surrogate models here. So we will have a first principle surrogate model. And for a cracker, we would train that with Spyro. We would train that with a simulator. So it could be a GPROMS, it could be an Aspen, it could be a Unisim simulator. And so this model is used to exactly replicate the nonlinear model that you have in order to design or optimize your plant offline. And this part we will never touch because the idea is the theory, and we don't want to distort that. So therefore we use the second model, which here is called the error correction surrogate model, to bridge the gap between what the theory says, what should be your COT or what should be your crack gas composition if we talk about a cracker. And this is something that we update basically in real time. So this is the way how it works. So we would run the first principle model, and this would say the theory says this should be your COT or this should be your conversion. But the reality typically is that your feed gas analyzer might not be properly calibrated. Your team had done some calibration of transmitters overnight. So all of a sudden the pressure or the temperature looks a little bit different. And so what we do in real time here, and this is basically the model on the right side, is we will, with every new data point, we will retrain the error correction model, which means you have the theory in the background, and at any point in time, with any scenario, any different feed, or whatever the condition of your plant is, you will have a model that basically matches reality. And this means you don't need a big staff that every couple of weeks would need to go into your Unisim or Aspen or a Romeo model and then basically tweak it. The same is, of course, the case if you have fouling. The same is the case if your catalyst gets a bit less active. And with that, we saw that basically the optimization performance was boosted. So basically the model always converges. Very nice. I think if you deal with kinetic models, you know about the problem. It takes seconds. So I think for a kinetic model for a furnace,
Thomas,
we take, I think, 200 milliseconds to run.
Sorry for interrupting,
and,
Thomas.
The fast implementation, no disturbance to operations, 50 to 7%, 70% faster, and of course, an automatic adaptation to any new operating cases. Thank you very much.
Thanks a lot. Thank you so much. It's really quite an interesting talk, and I'm sorry I have to interrupt you, Thomas, in between. We do not have time for questions and answer right now, but at the end of the session, please grab them and ask them your questions, note it down so that you don't forget. With this, I would like to invite now Jagadesh Donepudi. He is director with KBC, and we would hear from him another talk in the same line on plant operations with autonomous AI. Jagadesh, the floor is yours.
Good afternoon. Thank you very much for giving this opportunity to India Energy Week, and also to the audience for attending this lecture. I'm Jagadesh Donepudi. As Sir has mentioned, I'm from KBC Advanced Technologies. We are into consulting and software solutions. We have been in the business for last 40 years. We work with all the public sector and private refineries, upstream, downstream, etc. We are also a company of Yokogawa. What is our theme is like you move from automation to autonomous. That's the background of this, where we combine the process with automation, then go to autonomous. That's the sequence we are following. So my topic today is revolutionizing. When you say revolutionizing, really you have to come up with something very special. So revolutionizing with autonomous AI control. That's my topic. Yeah, I'll be covering a very sleek agenda. The first one is on the refining challenges. Then we look at some of the limitations of the current traditional control systems. Then we look at what is the AI mindset. Then we'll get into something very interesting. What is called is AI control with FKDPP. That is factorial kernel dynamic policy programming. That's the concept which we are using. Then we'll just get to you the normal implementation and then get into the examples where it is implemented right now. Just to look at the challenges. We are all familiar with the refinery. First, there are challenges with the feed quality, the challenges with respect to the feed availability. There is a volatility of the prices. Then, in spite of and also we are seeing a large amount of pressure due to sustainability. That's another aspect which we have to take into consideration to the design. In spite of all these things, you can see every refiner is running his plant more than 100%. And also they're looking at increasing the efficiency. So what it means is the optimization is continuously moving. It's not at a standard point or something. You make a model and it will stay there. So because the traditional control systems, they struggle just because the systems are getting very old. That's the reason. And also they're also looking at the complexity of the operations are increasing day by day because the interoperation among the units is becoming critical for us. So then look at what are the limitations of these traditional control systems. You have the normal manufacturing setup, you have DCS, then it is connected with the manufacturing execution systems like, you have historians, you have APCs, RTOs, then we're also connecting with some of the supply chain like planning, scheduling, and then to the ERP. But going forward, here in the normal conventional system or in the traditional systems, what we are seeing is a lot of intervention manually, but going forward, you will have AI control. You don't see a large manual intervention in connecting them. And the traditional control systems, as Sir has mentioned, I think in my previous speaker, the non-linearity is increasing and also the effect of multivariate is going up. So naturally, the processes are becoming more inefficient. The traditional control system is not able to capture those non-linearities, and that's why we are getting some of the suboptimal performance. That's the reason why we are getting into the AI. I'll just get to the AI mindset. Actually, if you look at the AI mindset, in the traditional systems, you have a relationship between the organization and the people. It's a one-to-one relation. Like you have console operators, you have field operators, they're trained in a particular way. And also it's becoming very difficult for an interchange of the operation. The skill is different from hydrotreater to hydrocracker to any other units actually. So the flexibility or the scalability is very limited. But when you get into the AI, if you implement some of the AI business processes, the first thing is like, what is AI? AI is able to predict actually. That's one of the reasons why we're talking about AI. It can predict, it can adapt, and also it can be autonomous actually. These are the three factors why we're looking at the AI. The moment you have these aspects, the important aspect with the traditional system is it is more reactive. The systems will be controlled from the reactive aspect, whereas since the AI control is more predictive, then you can respond to these dynamic conditions very well. That's the reason why most of the people are moving from the normal traditional control systems to something like AI control systems, which is like reinforced with some of the control systems what we have developed actually. So let me tell you what we are doing with respect to the FKDPP. So this is the factorial kernel dynamic policy programming. So a normal AI, it can be reinforced learning. It's very, very common to understand what is reinforced learning. You take a lot of data, you start computation. But when you apply that in a company like refining, you have so many units, so much of data, the computation becomes very enormous difficulty. That's the reason where we have gone into the factorial side, where it can address both the dimensionality and also the action spaces. That's what we have factored actually. That is the reason the factory, it's a kind of complementary. It's not that we are putting a different control system or anything. It complements you to your existing system. That's the beauty of that. And it forms a continuous optimization layer over and above whatever systems you have. That's where this FKDP can help you out. The implementation is quite simple. It's like, first you have to identify the areas where most of these PIDs or APCs doesn't give you the right results. That's the first feasibility we look at it. Then we collect the data, we develop an AI model with the historical data, and also we validate with the current data whether it is really giving the same idea. Then once your pilot model is validated, then we try to roll it out. When we are rolling it out, what we try to see is the current safety logs is not disrupt actually. That's the major point actually. The current, nobody want their control system to be disturbed actually using with another system. And the beauty of FKDPP is you can design this model with fewer samples. That's the very, very important aspect, because sometimes getting the data itself is quite difficult actually. We are seeing particularly in upstream cases or something where the data is very limited. And also it can be integrated with the existing control systems. So this we have implemented at a plant in Japan. It is running for last couple of years. It is a batch plant where you understand for a specialty, the quality is quite important. They were facing a problem. They tested with both PID as well as APC controls, but they never got the batch on process actually. We could get that batch almost 100% on spec repeatedly. You can see that it's already in operation for the last 2 years. And very importantly, we also integrated with their existing control systems, and this is working. And the kind of benefits, because we have implemented the loop of reboiler, they're controlling that more manually. So we could get reduction in the steam consumption, thereby the emissions, and also the 100% spec. So this is the kind of architecture you're seeing. Most of these controllers, AI controls, are embedded at level 2.5, which you are familiar, like, your current APC and historians are at that level. This is another controller which has got a bimodal communication. It communicates both with the DCS or the APC, and also it can read and write, and it can be integrated with any kind of DCS with the OPC systems. And also, you understand, when we talk AI, mostly we think the cybersecurity has to be compromised or anything, but we have taken that into consideration. It is implemented in the OT layer, not in the IT layer, where you have to communicate with the internet or anything. So that's how the cybersecurity is also taken care of. Then we have implemented in one of the oil and gas installation where they were facing a large amount of oil going out along with the water. That was, they were not getting a steady flow of the oil. We have implemented this. We could see something like, the variation of the flow was, reduced. Normal PID was giving something like variation 13.5, and we could bring it to something like 3.5. That's the kind of steady state where we could bring it with the AI application. Then I have some other examples where we have done recently with Saudi Aramco. Of course, they are published. You can always look at it, FKDPP, and you can get those references. But because of the time limitation, I just want to tell you in conclusion what exactly. So in essence, AI with FKDPP is a very novel thing. It is developed at Nara Institute in Japan. We have applied it. It is running, and it is stable, and it is autonomous, which is very, very important when you're looking at these kind of control loops. Then we have implemented, we find that the ROS is quite good. We could reduce both the steam consumptions, energy, etc. And what is my path forward? That's very important. I'm looking at is like we are looking at the autonomous controls are implemented across the plant to get into a smart manufacturing. That's the objective, and we are on the trial. Thank you.
Jagdish, thanks a lot. Really insightful. From the last two talks, we clearly see how AI is transforming the whole process control altogether. And it's not in theory. We have seen how real examples, real cases, we have seen the real return on such investments, right? Quantifiable gains. Really exciting. I'm pretty sure it will get more exciting going forward. So now I would like to invite G. Balaji. He's SVP for Energy Industries with ABP. And he's going to share with us how AI-enabled industrial software transform plant operations.
Thank you, Saptarshi, and hope I'm audible. When I subscribed to this topic, and then I saw the list of speakers, I understood that I'm probably one of the few business leaders who's going to talk about AI. So I'm not going to get drowned myself with technical stuff, but then I thought that I'll show and present few things about the human side of how an AI-enabled industrial software transforms plant operations. Industrial operations, as I see it, is as a crossroads between fading wisdom with a lot of workforce retiring and a huge explosion of data that's made available for the operators. The question is not, how do we scale up, but it's more about how we transform. AI is no longer a futuristic idea or an approach. It's more a practical tool that helps plant learn and act at industrial scale. The way I have structured this presentation is to talk about few challenges, talk about some methodologies, give some real life use cases where customers have benefited, and then a quick wrap up on what's been talked about and possibly the way forward. So if you look at the challenges, so primarily we see challenges coming from three areas. One is a succession gap. The second is on scalability, and third one is on reliability. And one of the facets it's an aging workforce that's retiring, and the knowledge and the intuitional knowledge that is gained over years of experience is somehow not translated to the new coming generations of workforce, and a lot of knowledge is lost. We also see a high level of automation across various industries, where industries that had few hundreds of sensors have multiple or many thousands of sensors. So that is a huge amount of data that is available. While human mind and intelligence is infinite, the ability to process this data to meaningful insights is quite constrained because of the divergence of the data and the divergence of how a human brain works. And that's exactly where AI brings structurization, contextualization, and then ability to crunch huge amount of data and give you meaningful insights. So we see that succession gap, the scalability with a vast amount of data, and reliability or core drivers of AI adoption in industrial use cases. This is probably a slightly different representation of the same framework that you have seen presented by the previous presenters. Typically, plant operations today operate between 2 and 3 levels, which is partial automation or a full-fledged automation, and it's more of a routine type of an automation. AI pulls you into level 4 or level 5 modes of operations, where the systems can handle complex scenarios much more independently. However, human oversights remain critical for both making both strategic and safety decisions. So the whole premise that we want to set is AI augments, it does not replace human expertise. So the methodology is about modern AI systems, which can, so as I talked about earlier, experienced operators tend to gain a lot of intuitional knowledge. So they know that when they're going to make a change in a process, what could be the parallel changes that could be expected. So a GPU accelerated algorithm analyzes this vast amount of millions of data and in sub-seconds, and then gives you meaningful insight. So the operator stands to gain a lot from historical knowledge in few seconds. Prescriptive then analysis then helps reduces the risk and bridges the succession gap. So the traditional control systems adjusts the set points without knowing the forecast or the cascading effects of a change. Intuitional knowledge, as I talked about, how an experienced operator gains. AI-enabled predictive simulators let operators test before they act. Simulators outcome shows the impact probably few minutes into an action being taken. This reduces the training time, operational risk, and supports augmented decision making. Few platforms that ABB has in terms of the plant insights and Optimax overlays the automation infrastructure, enables continuous optimization without disturbing the existing workflows. One of the key results that we have seen is in an ammonia plant where an incineration facility faces a varying fuel consumption depending upon the changes and then associated changes in ammonia dosing. So after implementation of our ABB Ability plant insights, we could see that there is a considerable reduction in terms of the fuel consumption. The ammonia consumption reduced by more than 30%, more compliances to the statutory regulations, and over more than 200 tons per year reduction in terms of carbon dioxide reduction. So this demonstrates both cost savings and environmental benefits. The second use case is more around FPSOs and complex plants. Complex plants requires quite an amount of manual labor and manual operations doing start off. One of the solutions that was delivered was a one-button start of an FPSOs, resulted in more than 5.5 hours saving in terms of startup time, and possibly in terms of mouse clicks, more than 3,600 mouse clicks. And if you add a further simulator, we had more than savings of 2,600 man hours in terms of startup. Now again, this is a classic example of how a faster and a scalable and reliable solutions can be achieved with AI adoption. The third case is more around energy transition. Energy transition requires both flexibility of production modes and so different source of energy mix. Optimax uses an AI-driven forecasting model for real-time energy management. This has reduced more than 1.5% cost in terms of fuel, in terms of the boiler efficiency, ensuring a return of investment within 1 year. Again, impact on both the environment and in terms of economic value to the operators. Key takeaways, we definitely see a core challenges addressed in terms of the generation gap, also in terms of ability to maintain operational performance in a changing workforce. Operational impact, real-time guidance, not just a post-mortem or a post-incident analysis. Energy transition value, balancing industrial growth with environmental responsibility. AI augments human expertise, enabling smarter, safer, and a greener operation. So way forward is definitely to continue this journey, building trust with more use cases, extended autonomy to be more, to have to consider more operational scenarios. And the message that we want to give probably is make human expertise more effective and not obsolete. So lastly, probably I would wrap up with saying that the future is not about replacing people. It's about empowering them. AI-enabled software transforms plants into a learning system where decisions are made informed by history, simulated for safety, and optimized for sustainability. And as I see it, the plants of tomorrow probably won't just run, they will start thinking. Thank you.
Thanks a lot. A great one, Mr. Balaji. Thanks a lot. As you have seen, right, in the third talk, we got to see how AI is addressing one of the biggest problems in energy industry, and that is succession gap. We all feel that jobs are reducing, but energy industry, power industry, they know this problem very well, that, hey, we do not have the core knowledge. It's so difficult to sustain the core knowledge, and possibly AI can help to address that as well. Now, with this, let me invite next Mr. Jaydeep Naha. He is GM Siemens Energy India. And from Jaydeep, we will learn more about digital brain and how AI-driven autonomous operations for asset management is transforming the industry. Welcome, Jaydeep. The floor is yours.
Thank you, Saptarshi. Am I audible? Yeah. So good afternoon, everybody. Just now we heard Balaji talk about the brain of the human. Incidentally, my topic is about the digital brain, which is what we are trying to take to the next levels. I'll try and explain in a bit as to what are we trying to do here when we talk about AI-driven algorithms. I mean, there's a lot of talk about AI. But let me start with what problem are we solving? So as you see that I'm from Siemens Energy, and increasingly we are talking about energy transition. There's a lot happening, of course, on the ground there, but that brings in a huge complexity also into our existing grid systems. We also, of course, have cost pressures. So we are not going to pay out of the bills for everything. Together on that, we heard also Thomas talk about shortage of manpower or experienced manpower in the world. This does not mean that we are asking people to leave. It's just that we do not have enough experienced people across the globe. And that leads to a lot of know-how which is getting lost. So when we talk about all of this, essentially if you just try and summarize that, you would basically see that we are fighting a much more complex situation on the ground with less people and a lot of pressure on costs. So the idea was try to look into how can AI and autonomous solutions really bring a solution to this. As you see here, to manage this challenge, one of the topics, I mean, this is just one of the levers, many levers that we are actually working on, is talking about autonomous plant operations. Now, when we talk about plants, this is not only just power plants. This could be oil and gas topsides. This could be a transmission plant, HVDC converter hall. This could be the whole plethora. So when we started this journey, we realized that a lot of people were talking about pushing a button or talking about AI agents, and we tried all of that, believe me. We figured out that, and it took us some time, that while we are developing this solution, we first need to specify where are we in a particular plant or in a particular operation. So Thomas talked about the 6 levels of autonomous operations. I more or less present the same thing. You can see from level 0 to level 5. What is very important here is to understand that when we start, not every plant in every country will have the same solution. And this is why we really try to first establish where are you with your plant, and then we take it to the next level. So Balaji talked about that most of the plants are in level 2, level 3, which is exactly what we see around the globe. So ambition of everybody is to jump to level 5. And we need to first understand that you cannot make that jump from 2 to 5 or 3 to 5 directly. We have to go through a stepwise processes. So here you can see some description of what these levels mean. And corresponding to each of these descriptions, you of course see what are the technologies that is already out there, or we are moving to the next levels. But I wanted you to focus on what I have written right at the bottom of the slide. You know, without high quality data, none of these things will actually work. And we tried. So one thing is to understand these AI-driven projects has a curve which really kicks off after 60% of the work is done, which is data cleaning and data structuring. This is where most senior executives already give up on AI projects, saying that my pilot is successful, but I'm not able to scale up. So I really wanted to bring you to note this point that if you have a lifetime of a project which is around 1 year, 2 years, the first 60 to 65% would be very, very boring, and you would not see results, because that's where we spend the time on data cleaning, data structuring. Of course, we need to have a very flexible architecture already to kind of scale that up. And last but not the least, right, you see at the center, it has to be an incremented, integrated solution. So let me try and see. We attempted to include a video in this presentation, if that works. Well, it does, but without the audio. What we tried to decode here is, you can see a power plant scenario here. It's an oil and gas facility. What we're doing in the energy transition process here is, because it's increasingly complex, we are managing critical infrastructure to what we call as the digital brain, because we have very limited resources for traditional operations, traditional maintenance, and we are really trying to break that through with what we call as the digital brain. Now, the digital brain comes with a robot, and again, we at Siemens Energy do not make robots, so we have a partnership ecosystem concept. But the whole idea here is that the robots are actually working in an ecosystem with the asset management. And you can see there are different modules like reliability, diagnostics, maintenance, and operations. When that happens, you could actually send out a robot from a digital brain with the AI-driven algorithms that we have to really convert very complex charts of what human beings do today and acquire the data set. If you see here, and by the way, this is an animation, but we have live examples of more than 10 plants across the world. The robot is going around collecting real-time data in a very structured format and sending it back into the operating systems. And you can see it is in a very structured way that we're getting that data. We are collecting that and making sense out of that data. So this is basically increasing our insights, and this is why we call it insight operations as well. So pretty much in real time, we are converting using algorithms as to what is going wrong, so that the whole concept of central control room functions is really, really empowered. Today, we can sit in India and run a plant in Germany, which is, by the way, what we do. You can see here also, we do not have to really rely on expertise in the location itself. And last but not the least, we have to have very, very stringent cybersecurity policies here. The picture that you show here is of a real plant that we were actually working on. So it's a combination of simulation, sensors, data, analytics, all coming together into a platform. And this is what we call as the digital brain. And it's not just robots. It could be drones. It could be CCTV cameras. It could be any IoT devices that you have into the plant, which is basically connected. You'll have real-time video feeds. You would be basically able to real-time also find out problems that's actually happening. And then optimizes using the algorithms based on the data that you've acquired at that point of time. You can see here in real time, we're trying to see if a valve is open or closed. It's a photo taken, and immediately the AI algorithm is able to say that it's open, which probably should not have been the case. When we feed that into diagnostics, we also make sure that the operator on the ground gets the result of what he or she really wants to do. So in a sense, that is what we call as a digital brain. It's basically a combination of what you see right at the center as an industrial metaverse. We are in partnership with companies like NVIDIA to do that metaverse piece for us. We're using drones, robots, any kind of devices to kind of gather data in real time. And at the bottom, you basically see the advanced analytics that we are running. Yeah? So what it is essentially that we are modeling, just like a human being has eyes, ears, nose, hands, We're basically modeling that around sensors. So it's a combination of sensor technologies. Of course, we're using machines. That could be a robot, but we are also using machine learning algorithms. And the most important piece here is the intelligence that we are giving it here to the brain. It's learning all the time, just like a human being does. We say that we have like 20 years of experience. That's a lot of learning. So we need to feed the digital brain data. So what we've done to begin with is to collect data of how the human being is doing the job today. So where to go, what assets to visit, to go to asset number ABC to do task number 1, 2, 3. Pretty much, because on its own, a robot or a drone would be pretty dumb. And once that data comes in, we're integrating all the existing workflows that we have today. So it's a digital workflow that is integrated across these systems. And then we're making sense out of that at the same time. So you can see that how this is really connected to what a human being really does, because all that is information on the left-hand side is fine, but our colleagues are always telling us, so what? So how do I take the next decision? Where do I move? Should I stop the operations? What if there's an emergency? So that's why we're connecting this to our asset management suite, and we've kept this completely open so that this workflow can be bidirectional as well. So the whole concept here is to close the circle without a single human in the loop, as you saw that. So it's truly autonomous. And we, of course, we are testing this with a human in the loop because we're dealing with critical infrastructure. But the whole idea there is based on the advanced analytics. So what you see here is it's connected to the checklists that are used today. So we've kind of digitized that and put that back into the brain. So at the bottom, you can see that it can work on any asset management. So this is an open platform. It can work with any analytics repository. So we are working with a lot of startups across the globe to come into that. Gone are the days when we just say that, hey, this is our IP and we stick to it and we do now more. We've learned that if you open this platform up, there's everything, a lot of things for everybody. We're also looking for the robots and drones to be totally hardware agnostic so that we're not really married to one set. Then we're converting it into where to go and what to do. We are also telling it the asset locations. This is where the digital twin actually helps, which is already in the metaverse that we have. And last but not the least is we are, you can see at the bottom also, it doesn't really depend on which cloud you are. It could be on premises. A lot of our plans, especially in the Middle East, for example, the data cannot leave the premise. But it's difficult to train the models, of course, there, but it's still done on premises, but it can be done on any cloud. It could be the cloud that we host. It could be the cloud that is hosted on our customers. But eventually, it should be any robot, any cloud, any startup, any academic institute, any repository, and any startup. And then that's the whole idea of how we really take this forward to the next levels. And this is what I essentially wanted to also kind of showcase here. So the integration piece is very important. We coming from the domain knowledge piece, this is very important that we are able to kind of integrate the intelligence. The intelligence is really the domain knowledge of the assets, because without that, a lot of software companies want to be in that white space, but they can't because of that domain knowledge specific. What is very important, and this keeps us awake in the night, is there are a lot of cyber threats. In recent years, we are seeing a lot of cyber physical threats as well. So we have to take that into account so as we do not lose face of all the major customers that we have, which are essentially governments of different countries. We are also able to kind of operate this offline without the internet. In today's geopolitical situation, you can imagine what happens if we just depend on something or a particular technology. So we've also made the digital brain completely averse to what we call as the internet. So it could actually operate offline, and it works interchangeably. So essentially, the brain is right at the center. It is able to work on any cloud for the cloud intelligence. It is able to work on any analytics repository. It could be video analytics. It could be plant analytics. It could be real-time analytics of images. We're pushing that data back into the digital brain, and this is how it learns. We run these AI-related algorithms repeatedly. After that, we push it into the asset management, because at the end of the day, all that on the left-hand side need to make sense for an expert to make a decision. In this case, the expert is not a human, it's the AI agent, which is in the asset management. And then we also created APIs where any independent services can join the wagon if they have a particular expertise in certain areas. Yeah. So the key highlights really is around the orchestration of what we do, the intelligence pipeline, because this is as many assets, as many plants that you will have on the plant, it'll keep on increasingly, and then the integration piece, which is, I must say, not the easiest. Yeah. So I just want to conclude, what do we gain out of that? And that's exactly what was my first slide. It saves time. We're talking about more than 1.5 to 2 times. Of course, it reduces cost. We have to increase the trust level. A very important aspect is the integration of the data. So you can see that today, human beings are wasting a lot of time in trying to pull data from different sources, from manuals, from colleagues, and that's something which is done in a press of a button at the moment. And all of that, on top of that, we are running the AI algorithms. It reduces risk because you saw certain examples where we could actually send this out to hazardous equipment areas so that the risk to human beings is also reduced. It avoids hassle. And last but not the least is, of course, that it informs about the location, because nowadays we get increasingly use cases as to bail out a human being if somebody's in trouble in real time as well. So essentially, the digital brain is actually an overarching map which comes to address the main use cases. And there are several use cases. We talk about the digital operator rounds, which is nothing but the same thing that humans do today in plants, both in inspections and in actual operations. But with the digital piece in place, that means you do not have to do that physically. And then there are EHS factors, which also works together. And last but not the least, there's also something which is very important, the human element in all of this, because, you know, in most of the plants, in most of the countries that we actually deal with, we initially got a lot of pushback from the colleagues on the ground who think that they will lose their job if they do this. And so the human factor is very, very important to make sure that this is not happening. And this is a change management process that also needs to be there together with the entire technology. Thank you.
Jaydeep, thanks a lot. We learned a lot from your experience, right? And as you rightly said, you tried many things, failed, and actual learning comes from failure. And then you shared with us what really worked. This session is getting interesting, isn't it? We started with control and how AI is helping with the control part. Then we moved on from control to more towards even deeper problems like succession gap. And now we came to even more where we talked about the whole plant, looking into all the risk, cost, everything that can be addressed using digital brain. So as it's getting more exciting, I'm pretty sure the next one is going to add on top of that. And with that, I would like to invite next Medini Kumar Bora. Medini is a senior manager from Numaligarh Refinery, and he is going to share with us the role of digital twin in autonomous refinery operations. Medini, the floor is yours.
Okay, good afternoon, everyone. Respected chair of these sessions, distinguished delegates, and my colleagues. Today is my privilege to be here at 4th India Energy Week. When I joined NRL, that time I was very curious about how the control room engineers manage lot of screen, vast of amount of data and alarms. But now when I enter our refinery control room, I often ask one question. After 10 years from now, what if our control room engineers are refused to work at night shift? What if our maintenance engineer switch off their mobile at midnight? If I calling that my pump is not working, can you help us? Can you come us? If they did not pick up their phone, then what is the solution? That is the question. If you have this type of question in your mind, then we are in the safe hands, and I should not be lot of stress in these topics actually. And to address this problem, we must redesign our works. So machine handle the execution part, and a human, as we already speak about that, what is our limitation? We have to accept that we have a limitation. We cannot compete with our computer. So we must focus on the judgment and decisions. So that's why today I will speak about the role of digital twin in autonomous refinery operation. So let's begin. Okay, here just I want to show all the autonomy level 1 to level 5 already described by my previous speakers. Now I just from my engineering, I'm actually engineering background, so I very much understand in the visual context. So I have used AI to generate what will be happen in the next 15 years. Just have a look. If you see current situation, if you go inside the refinery, lot of screeners there. Lot of engineers are sitting here like that, and everybody is alertness. If something happen, I have to react. Something happen, I have to act. All that day in day out, they have doing the same thing. But what I want to stress here, after at least we need some smart engine or smart machine, so that we can achieve a good autonomous system in our refinery across. So in this section, let's see how digital twin will help us. So at least humans should focus only the judgment part. Like say you can what will happen in the next 10 to 20 days, or why we are producing SSD, or why we are producing ATF. That type of question we should act on that. Let's see the next one. So why we are talking about our autonomous operation by 2040? The main driver is the safety and risk mitigation. If you analyze all the incident, this is not lack of sensor. It is, if you see that we did not get the data in that on time. If you get the data on time, then we can definitely reduce all the safety point, and we can manage our plant safely. Then next point is economic efficiency. At least economic efficiency, if you see, we are not able to operate a plant by manually adjusting the parameter from optimum level. So this is one of the main driver. And last one is global competitiveness. Global competitiveness, here I want to stress is that the country that those are implementing the autonomous operation, they will be the next future cost. They'll benchmark the future cost benchmark, and we have to follow them. So counter this, and we have to, from India side also, we have to adopt some initiative so that we can compete with the global audience. So what is the next question is whether autonomous operation is really happening in the ground or not. Let's see. Okay, if you see this, I have collected only the few sample set from the developed countries, Japan, Saudi Arabia, USA, China. If you see that they are already on the tracks, and if you are not, we are not able to convert our old system, then we will be nowhere. And we have to sustain in this next future refinery operation, we must adopt the autonomous operation. Okay, but as I am just a senior manager, so I don't have the authority to see what across our oil and gas energy board in the board room, what the discussion is going on. As a from a senior manager, just I have one good source that I have annual reports. I have collected all the major oil and gas industry Indian, I have collected and I have filtered out the keywords. The digital, like if you see the digital digitization, automation, digital twin, agentic AI, and I have see that the graph is looks very impressive. And I am confident that if we pace in this direction, definitely we will able to achieve the autonomous refinery in by 2040. My previous speech I already shown a good video on digital twin, how digital twin collect the data on how they will what they are doing. Thus, I am just giving one scenario. Suppose next 5 years. Suppose you are operating a very low sulfur crude oil and very low API crude oil. Suppose next 5 years. Suppose there is one situation. You have to run your existing pump with a high sulfur, high API crude oil. Then what will be your answer? Suppose from our main as a human, we have the intuition that I'll check the data sheet. Data sheet is not allowed to operate this pump beyond this range. But can we say that this pump can operate next 4 to 5 years? Provided I have to change the impeller or bearing, but the shaft. That type of question, if you not able to visualize this type of data-driven decision, we are not able to add to the value to the company. So what I am trying to say is, digital twin is a very simple concept. If you see the physical structure, the figure one. Figure one is just a centrifugal pump inside the pump. We have seen all the centrifugal pumps, and they have a lot of sensor, but sensor give the data, but we cannot see what is happening inside the pump. So that's to counter these things, we have a engineering model, CFD model, and FE model. The problem of the current CFD and CFD model is that they not able to give my result in real time. So real time means the current context is that they have a convert at least more than 100 or 200 parameter convert to predict the output. So what the current limitation of our computing power. So we have to reduce the 100 numbers of at least per sec. 100 numbers we have to reduce the dimension have to at least 10 to 20 meters, so that we can easily get the real output, real time data we can from this formally computed model. So that final model is called digital twin. That digital twin model run along with the physical structure, so that what the digital twin is know that what should happen and what is not to happen. And with the digital twin, we can give a lot of prediction. We can do it. Time is running out actually. Okay. These are 5 critical rules played by digital twin: design and simulation, predictive maintenance, and workforce transformation. Now coming to our NIL digital twin implementation, we have recently implemented one process digital twin in our crude preheat train with our partner, with our Aspentech online. Aspentech, what our problem has solved by our vendor is that we have before implementing digital twin, we have lost around 5 to 6 degree preheat temperature in our refinery, but we could not be resolved by manual calculation or manual Excel observation. So why we have approached Aspentech that we have this whole problem. Can you help us? Though definitely they have helped, and they have nicely our implement one process digital twin. So as you can say from our as a operating refinery, we are very much confident that if we do a lot of collaboration with our industry across, then we will definitely able to solve a lot of problem. This is just the one where digital twin structure. One plan DCS is collecting the data and store in the data historian, and now we process pass that raw data to the S-Pen online, and we filter out all the outliers, and we pass it to the process model. The process model that knows that what should be the happen and what is going on, and operator only see that which exchanger is having problem and what is the trend. That is our as a operator, our option, our motto is that what is happening inside the what of calculus, a lot of calculus, we are not bothered about it. This is the annual benefit we have realized. We have able to reduce, increase our cold pit temperature by 6 to 9 degree. And the good thing is that we have achieved the rate on investment less than within one year. And we all know that in a single shot we cannot achieve the autonomous operation. We have to be phase-wise manner. We have to implement our autonomous journey. So for discussion, I have categorized in the three category: full autonomy, up to from foundation to full autonomy. In the foundation model, we have to develop our people mindset and people skill set also. And last one, what I want to stress is there, we need to convert our control room to decision center. From control room to decision center, so that we can utilize our human judgment. By implementing the autonomous operation, we have received a lot of opportunity. Before Viksit Bharat, before entering, we are entering to the Viksit Bharat area. So if we approach in a good manner, so that we can leverage our India IT strength with the deep oil and gas industry expertise, and we can export our digital knowledge, digital refinery knowledge to the outside world. This is my team member, Mr. Amitabh Bhattacharya, Mr. Pandajoti, and myself. And autonomy is just is not a solo act. We have to be. It is built on that trust, discipline, and collaboration. This is the. Before I conclude, I have one thought. If you have heard about that RBI report, Assam has recently had the fastest growing economy in the country. So on behalf of my team, I request to visit Northeast at least once and experience its culture and people and natural beauty. Thank you for your time.
Thanks a lot, Medini, and surely I will visit, for sure. And thanks for enlightening us on your journey with Digital Twin. So with this, we learned a lot from this session, really exciting, really insightful. We started with how AI is helping with the control. Then we moved to other critical challenges of oil, gas, energy business, including addressing succession gap, addressing cost, data security, and finally we have learned how we should think from digital twin perspective to put everything together. With this, I would really like to thank all the speakers for sharing your knowledge. I'd also like to thank all the audience here for listening. And now I'm pretty sure, like me, you also have a good lot of questions that you would like to ask to our esteemed speakers. Please take the time, grab them, and I hope you will have a very good discussion around this. Thanks a lot. And with this, we conclude this session.